So emulating that correctly would be a dumb approach in terms of prevention. What we can actually do is what we would do in dynamic analysis. In dynamic or runtime analysis, what we would do is we set a breakpoint somewhere in a code saying, this is where it actually happens. Here, all the arguments have to be assembled already. Like whatever obfuscation you did before, at this point in time, the argument, like the URL for redirect, must be correct. It can't be obfuscated anymore. We set a breakpoint here, and then we see where the URL is, and then we know what it does. However, when the code runs, we're no longer part of the show. We already handled the Swift file. So what we do is we actually patch those functionalities into the Flash file once we handle it. How does that look like? So there's an instruction called action get URL2. Yes, it's version 2 of an instruction that used to get to a URL. And that's the most common way for the browser redirects to work. When we get the Flash file, let's say we're running in the context of a web browser or proxy server, we actually know the origin. We know where it came from, right? So we can actually implement the same origin checks in the way they should have been implemented on the original runtime. And this is how that looks like. If you take like a regular piece of code, this piece of code in the middle here, the block is called ID31. Actually does have a get URL2. You see before, remember it's a stack machine, so you actually have to put all the arguments on the stack before you call an instruction, right? So this one here puts the arguments on a stack. It's a trivial case, it takes it from the constant pool. We're going to talk about this later. But there is a specific place where the instruction is actually going to be executed, right? So at this point in time, we know where it's going to go. So we actually patch the code to compare it with the origin that we came from. It essentially, what you see in the orange, it used to be orange on my screen, in the orange blocks, they got changed. So you see that the action get URL is actually one of two possible conditions. And you see, like, it's denoted 31.6. There's an action push that actually pushes the original origin that we're actually dealing with right now on the stack. It's Google in this case. It's the friendly version of Google, you know. They don't store data, they don't Vorratsdatenspeicher, Sie wissen schon. Anyway, so in case it doesn't match, in case the strings don't actually match up, it will just pop the arguments, the original arguments for action get URL2 off the stack and behave as if nothing happened. Otherwise, if they match, then we can actually go to the URL. Isn't that trivial? So, what do we need to patch? Well, Adobe published a list. Actually, PLS published that list in his secure development guide, and he's actually here. So, publish a list of functions that are potentially evil, where you could potentially have issues with. Functions that, or objects that accept URLs as strings, obviously push you to other websites or pull stuff from other websites. Functions that display or accept HTML. So there's text boxes in Flash, which Flash developers commonly take text from anywhere and put it into the text box, which is a relatively bad idea because the text box actually renders HTML, which includes JavaScript, which then, you know, makes it all interesting. We have a couple of functions that communicate with the web browser. We have flash wars, which, yeah. We have shared objects, local shared objects, which is also known as flash cookies. So you have a local storage that's independent of the browser, and no matter what browser you take, the porn site will recognize you again. And we actually have flat networking calls. This is all stuff we potentially want to patch. We also want to patch stuff that is not documented, like ASNative. ASNative is this brilliant function that you can call. You pass two numbers to it, which is a lookup in a table, and it will actually return a function reference to the native function that is behind this. So in this way, you can totally hide what you're doing. I also found cases where it does very interesting things. So how do we do actually patch? So our beloved Blitzableiter tool actually features an AVM1 assembler. So you go ahead and you say, if you see the following instruction in the following context, I would like you to patch it with this. And I would like you to make sure that you stay within the same basic block, that you fix up all the offsets, that the code is going to be valid afterwards, which we actually ensure by running every Swift that we modified. We run it twice through the engine, which is optional. But like the second run actually verifies that the first run didn't fuck up anything. So we do support all the 100 documented AVM1 instructions, and we also have support for variable names. So you can actually write code and say like, do this and that with $origin instead of writing an individual patch for every website you visit. And it also supports randomization of variable names, which is like the cheesy virtual machine way of ASR, because like the moment you put out a tool that has a variable that says check if evil, and that variable is called the same thing, the malware would just check whether that variable exists and set it to false, obviously. So we actually have to randomize the names. And then it gets interesting. Like most of the things we actually want to patch are calls to methods. So here we have an example. When a call to an object method is made, you here see a action constant pool, which defines the constant pool. And yes, every single instruction starts with the word action. I felt like a director writing this. So that actually, it pushes the variable name and the method argument individually on a stack. And then it says get variable, which retrieves a object instance pointer, which is then put onto the stack. And then it actually pushes the string of the method and says action call method, and then hilarity ensures. To actually figure out what there is, you first have to swap the stack, because first you want to get the object reference, take the object reference, get an instance of such object, compare whether those instances are there, works since Swift 6 or 7, and then like exit a patch if that's not the type of object. If it still is, then check the method and then like clean shit up. Clean shit up is interesting. Like, how do you make stack cleaning in a stack virtual machine? I'm not going to go into the full detail here because that's going to bore everyone. Already see people yawn. But essentially, it's really interesting to do a stack cleanup within the virtual machine, within a stack machine. This is how you do it. So you essentially pull all the arguments individually off the stack and then pull the function itself and then return undefined, so the calling code actually thinks it actually called something. Oh, and here's the good thing about like the patching approaches. The patches don't have to be perfect. They should be logically sound. But they don't have to be perfect. Because the AVM is so forgiving in what it does, you can easily fade half of the variables to setting like, the type undefined. Shit wouldn't crash. If the AVM will actually be implemented like every sane virtual machine, they wouldn't have a customer base anymore. So the virtual machine just ignores every glaring programming error it finds, as long as it can safely continue to make blinky objects. So what we see here is an example of the famous Gnida malware. To the left, the blue thing, that's the regular basic block graph of that malware. It actually only has one code location. What you see to the right is the same malware, and the little red dots that you see in there is all the shit we patched. And then on top of this, you see the structure that was introduced above the white bar. That's actually a function that we introduced that does all the object checks, so we don't have to patch them in each individual place to keep the code inflation down. Now, what does it actually do? So we've added a couple of malware samples. You see it's only 20. Because it's really hard to get to actual Flash malware samples, because they're usually hosted by advertisement hosters, and at some point in time it becomes really boring to click reload on porn sites. We had like 20 unique things that did unique things, and not just all redirected your browser somewhere. So if it's AVM2, right now we can either let it go through or drop, because we don't support that yet. All exploits that were actually targeting the runtime itself, like Mark Dowd's exploits and all other incarnations, they all fall